we'll give people a minute to gather themselves, and then we'll get started in another couple labs. We'll walk through a simple quantum machine learning example, and then we'll go into a little bit more detail about something Dave's already talked about, which is tensor networks and our solution for accelerating the computation of tensor network calculations. All right. All right, so let's get started. So there's been some questions about getting access to these notebooks. The team will talk about options for doing that. Right now, they're available via our Deep Learning Institute, and we'll see what else we can do to make that more widely available. The container that's called our cuQuantum appliance. This is available. You can just pull this down. There's other ways to install cuQuantum, but the container is the most supported way. And if you pull this down, this has Circ, which you've seen a walkthrough of, and cuQuantum all installed and optimized and ready to go. So this is our recommended way of running this. So I'm going to start by walking you through a Penny Lane example. So Penny Lane is a package, an open source package put out by Xanadu here in Toronto. By the way, I'm Jonathan Dursey. I'm a senior solutions architect for NVIDIA based in Toronto, and my background is really in accelerated computing fairly broadly. So we are going to walk through this example. Let me get something started first, because it'll take some time. All right, so Penny Lane is about variational quantum computing. This is going to be a machine learning example, but the same variational approaches work very nicely for a number of problems in quantum chemistry. So for instance, the variational quantum eigensolver that Dave talked about a little bit. For these variational methods, and especially modern machine learning methods, there's some mathematical connection to quantum computing, right? That they have some similarities. You build, rather than sort of top-down algorithms, you build circuits which are based on layers of differentiable operators. They're often probabilistic in nature. In quantum computing, the operators are all linear, but nonetheless, there's some connection there, and there's some thought, and in fact, we'll see it works, that you can build quantum machine learning circuits quite effectively. So Penny Lane, we're going to import Penny Lane as QML, quantum machine learning. Penny Lane has its own wrapped NumPy, load an optimizer. We're going to create a circuit, and it's going to have one or more strongly entangling layers. This is, if quantum machine learning interests you at all, Penny Lane's documentation is really quite nice. These entangling layers are going to look a little bit like the highly entangled state Dave walked us through with Circ. So we're going to build our own strongly entangling layers. And at the end of the circuit, we're going to, this is just a quick demonstration. We're going to return some observables, some measurements, the expectation value of the polyzide matrix, so measurement in the computational basis. So when we can run this on the CPU, we get some result. That takes about 2 minutes. We'll talk about the Jacobian here in a second. So one thing I didn't point out about this circuit is it starts with this decorator, something about a CPU device. In Penny Lane, units of computation, like functions, are quantum nodes. These nodes could be running on a quantum device, and you have a number of different types of actual quantum processing units, or it could be running on CPUs. So the device we chose here was Penny Lane's, very well optimized CPU simulator, qubit state vector simulator, Lightning. We also created a device, a Coup quantum device, a lightning.gpu. This is their GPU accelerated state vector simulator, which builds on Coup quantum, just as you might build on Coup BLAS or other optimized BLAS routines. So when we run this same function with Coup quantum, we're going to see it takes significantly less time. It's exactly the same thing. We set up some number of entangling layers with some weights that we've set above. We do the same expectation value around the polyzide gate. And in 20 seconds, instead of almost 120 seconds, we get the result with 24 qubits. Maybe I'll point out here, in Penny Lane, we talk about wires rather than we talking about qubits. It's just a different terminology. Xanadu's own quantum device is a photonics-based one, so they tend to talk about wires. But these operations we're accelerating here are very fundamental, and they apply across sort of different simulations of different kinds of systems. They apply perfectly well across different sorts of problems on these systems, and they apply across different frameworks. We're going to see 3 frameworks here before we're all done today. So now let's solve an actual quantum machine learning problem, a variational classifier. So let me go down here and show you what the problem is we're going to solve. So we are going to teach a quantum circuit to reproduce the parity function. We are going to give it a series of x's, a series of input data, 4 bits, each of which are 0 and 1. And we're going to teach it, and they're labeled with y, and we're going to teach it to reproduce this y function, the parity function. Returning the convention here is a -1 if the number of ones in x is even, and +1 if that number is odd. All right, so how are we going to do that? Well, first, we're going to create a device. We're going to have four wires, 4 qubits here, because we have 4 inputs. We're going to build a layer here. We're going to build our own entangling layer here that takes, for each of these wires, applies rotations around each axis of the block sphere and C-knots them together for entanglement, well, now that they're superimposed. So that's the layers, internal to the circuit, the hidden layers, if you like. There's the state preparation. We need to prepare the input state of this circuit corresponding to some x. We're going to use a built-in function from Penny Lane basis state for that. I'm just going to take this array of inputs and put them out across these wires, these qubits. And the single bit we're going to read off of this, the output we want to train, is again a measurement, the expectation value of a polyzide gate on wire 0, on qubit 0. So the circuit takes this prepared input, applies one or more layers of these entangling layers with these parameterized rotations, and returns a single measurement, an observable. All right, so those rotations are going to serve as the weights in this machine learning algorithm. If we want to bias, we sort of, that's a little awkward to plug in here. So we're gonna do that on the classical side. So our variational classifier will be a hybrid system. We're going to run this quantum, in this case, quantum simulated circuit, and add a single bias parameter to the output. And this is our entire variational classifier. So it is a hybrid circuit. All right, so we have input, we have the circuit returning an output. Now we need something to optimize and an optimizer. And we have the fundamental pieces of a machine learning algorithm. We're going to, because we're returning, expectation of the measurement in the computational basis, it's going to be +1, -1. Our label for each of these things is also going to be +1, -1. We'll just use the square loss as the loss function. So if we predicted a 1 and the output is a 1, then the loss is 0. If we predicted a 1 and the output's -1, then the loss will increment the loss by 4. And the accuracy is almost the same. We're just going to count the number of times we confidently, very confidently, made the right prediction. And there we go. So the total cost, as we put a number of inputs through the system, the total cost is going to be the square loss of all the predictions. We're going to make predictions on all the x's, compare them to the y's. So we have the state input, we have the circuit, and its output. We have a loss function. We've got the input data. Now we're ready to run this. So we're going to generate some random weights. Here we're going to pick, we're going to have 2 layers of weights, each one applied to all 4 qubits, 4 random Gaussian, it turns out, normal random numbers, rotations around each axis. So those are the weights. That's the bias starts at 0. We're going to choose one of a number of optimizers from Penny Lane's library. This is a gradient-based operator with a momentum, but there's many to choose from. And now we're going to do the training. So for each number of iterations, we're going to take a batch of inputs and the corresponding outputs, step through the optimizer. We've given it the cost function, which includes the circuit, the input weights and biases in the batch. Going to get some updated weights and biases out. We'll make our predictions, and we'll use this circuit. Now we've got the weights and biases to make the predictions and check the accuracy. We'll just generate maintain a log of those. And now we can see how the function works. And very quickly, after looks like 5, 6, 7, 8 iterations, we've completely nailed the accuracy, getting everything predicted exactly correctly. It took a little bit longer for the cost to go basically to 0. Even when we were predicting them correctly, we weren't predicting them 100% confidently. So now here we go. We have now nailed the cost as well. So this is it. This is a simulation accelerated with cuQuantum of a real but simple quantum machine learning algorithm. And again, if this interests you at all, if you want to find out more, again, I commend to you the various demonstrations in Penny Lane, the tutorial materials, videos, and just just in the quantum machine learning section, they have a lot of really cool stuff in here. And a lot of this stuff also carries over to their quantum chemistry, packages. So that's it on Penny Lane. What sort of questions do people have on this in particular? All right. So I'm not seeing any meetings on this. There's a question about nonlinear gates in cuQuantum, which I don't know the answer to. Jinsung will be back in a half hour, and he's exactly the right person to answer that question. So I am going to go on now to talking about cuTensorNet. Again, something quite different. Let me go to the slides and give a little background information here. So, all right, tensor networks. Some of you will have already seen this. Some of you won't. You may be familiar with tensors. If so, great. If not, also great. We'll talk about them a bit here. So tensors can be thought of as a generalization of matrices. They have some properties under transformations. A matrix has two indices. A higher rank tensor can have multiple indices, an arbitrary number of indices. Here we see a tensor of rank 3. It has 3 indices into it. So tensors sort of unify vectors, matrices, and higher rank objects. They can be represented rigorously, diagrammatically, like this, when we are operating on when we operate on them. And in particular, the fundamental operation between tensor objects, a contraction, can be seen by joining an edge. So a vector is a tensor object of rank 1. It has one edge leading into a node in a graph. A matrix has 2 indices, 2 edges leading into a node in the graph. Tensor rank 3, 3 indices, node. Here we see 2 tensor objects, each of rank 3, with a shared edge k between them. This is the same. This is another way of representing this summation over k, aij k, b mkn. This is a perfectly rigorous and very useful to the intuition way of describing this summation. If you are familiar with tensors, you're likely also familiar with Einstein's summation convention. If not, that's okay. That's not rocket science. You can get rid of these summations, these big sigmas. They get a little tedious after a while. And the convention is that repeated indices imply contraction, so that we just sum over aijkb mkn. So this Einstein summation notation is another very handy way of representing these tensor operations. So this is yet a third way of representing the same the same operation. So if we contract ijk mkn, again, the repeated indices imply summation. So this produces as an output some tensor object with 4 indices. So we perform this operation on the tensor objects A and B. And this is a third way of representing this system. Okay, so awesome, cool. How does that help us? So Dave described a state vector representation of a quantum system, quantum circuit, which is a lovely and very natural way of simulating and maintaining all the state all the way through a circuit. Another way is to represent it as a network of tensor operations. So we can think of these 3 input qubits as rank 1 tensors. We can think of these single qubit gates as rank 2 tensors, multi qubit gates as operations defined with tensors of higher rank. And so this entire circuit can be rigorously described with this graph. And where this helps us is if we can't or don't care to maintain and simulate this, all possible states everywhere internal to the circuit, we can just start performing these tensor operations, start performing these contractions, and be left with a much smaller system, an easier system to keep in memory, an easier system to simulate at the cost of no longer having visibility into some of these internal states. So this is the tensor network. These are lovely but sneaky systems to deal with. So let me jump back to a slide Dave showed and walked through just because I like it so much. Dave walked through this already. I'm just going to remind us because it's going to be very relevant for what we're going to walk through. Even just a simple linear chain of matrix or matrix vector operations, you can make much less work for yourself, both in terms of the computation and the size of the intermediates you carry around, if you choose wisely which pairwise operation to do first. We don't have the option of flipping B before A, but we can do, BC and then AB, or we can do AB then AB times C, right? So we have the order of these pairwise operations we can do. And if, in the simple case, just a chain of matrix or matrix vector operations, if we do these inner products first, these are very small computations. We end up with scalars, which are very easy to carry around and multiply. If we do these outer products first, now, we do a lot of computation, almost all of which is going to be projected out, and we're carrying around lots of additional intermediate data. So that is for this simple case of a linear chain of objects with the same rank. When you start getting into systems that are more complex, it is much less obvious how, in what order to do these computations without having everything blow up on you. So cuTensorNet is the part of cuQuantum that handles these. It has a fair amount of work that's gone into the algorithmic work, implementing the contractions, doing the contractions very efficiently on the GPU. And we've seen this slide already. It's broken into multiple phases. So let's talk a little bit about what this looks like. So we are going to use here a third quantum framework, QUIM. So QUIM is a framework specifically for quantum information theory, leans very heavily, has a lot of really good work on tensor network computations in particular. And we are going to load one of the family of Sycamore circuits that Dave talked to. We're going to load that into QUIM. So this is a fairly complex circuit. There's going to be, Dave mentioned, 53 qubits. We're going to create a random bit string of length 53. And with this circuit, we're going to create a network that basically just overlaps the output of the circuit with this bit string B. So this is going to look something like the amplitude of B. So let's plot this. So this results in a quite large network. So 1,700, almost 1,800 tensors, getting pretty close to 2,000 indices in total. So we end up with this lovely but somewhat intimidating structure, and it's certainly not clear. There's no single order to contract this that immediately jumps out. There's some things that QIM can do to help us, so it can simplify this circuit a little bit. We'll talk about how that works in a moment. And after we perform that simulation, we can plot it again. We're down now to perhaps a more manageable 164 tensors, 300 some odd indices. And we get this graph that represents this series of tensor computations we're going to have to do. We mentioned Einstein summation before. We can express this series of contractions in Einstein notation. So we get the arrays, the actual tensors themselves, and express this in tensor in Einstein summation notation. This is exactly the same thing as that graph. You see, with a tensor network of this size, we very quickly run out of English letters. Latin letters start having to use Unicode characters, but it's exactly the same. This is the same as that graph. So we can contract this. So we're going to load from cuQuantum, import everything. We're just going to perform this contraction, look at alpha and alpha squared, so the amplitude, the probability of alpha's amplitude, or this is the probability of obtaining B, and that's it. We end up with this very small number, and that's a very maybe not very exciting conclusion. So let's take a look at what's happened here. So we have just run this entire setup on that quantum tensor network in one step. So let's dig a little bit closer and a little bit more deeply into the various steps that happened. So we saw something about the simplification. We relied on QIM for that. We'll show cuTensor network handling this in a minute. But a very common first pass is to reduce the size of the network we have to wrestle with through some pre-processing. So, for instance, here, if we have chains of pairwise contractions that aren't going to increase the rank of the resulting tensor, we can identify them as first paths and just contract them. They're not hurting us. They're not increasing the rank, but they do simplify the graph we're going to be working with. So we can perform that iteratively until we're done. Then the heart of the Pathfinder algorithm is this divide and conquer, this divisive algorithm. We're going to recursively partition this graph into subgraphs until we get subgraphs that we can exhaustively search, or we have really good heuristics for finding a good path for. And then we can start stitching those paths back together to find a path through the whole graph. This, depending on the size of the graph, we may want to split this up into separate chunks to slice these operations so that they can be solved in parallel, or so that we can pull chunks in and out of memory. So slicing is a technique to basically pluck one of these edges out to the outermost loop of the contraction, and then the loop over those indices can each be a slice that can be farmed out to multiple GPUs or be done in multiple stages. So it allows for lower memory requirements and/or parallel execution at the cost of some overhead. If tiling of matrix operations is something that speaks to you, maybe you can think about it like that. It's not a perfect analogy, but it's the same kind of idea. And finally, there's a reconfiguration step. So we've to try to shake up these subtrees we've gotten. These are sort of semi-local optimizations to reconfigure this set of subtrees we've got, try to move things around and see if we can find a better solution. So those are the different steps of this optimization phase. And then the execution phase actually performs the contraction. So, in many contexts, Dave already mentioned query planning. You could think of creating an FFT plan if that's the sort of thing you've done. It's doing some pre-work to make the actual work go much, much more efficiently. And typically it's worth spending a lot of time on pre-work, partly because the execution is so expensive, but also because you're typically not going to execute once. You're not going to do one computation with the circuit, often say, yep, done, and close the window. You're typically going to perform lots of optimization, lots of calculations. So spending some significant amounts of time on the pre-work can often be worth it. So let's dig a little deeper then into this contraction operation. So what we did is we had this representation of the graph, this summation, and we have the actual tensor arrays, and we called contract with that expression, with this set of the actual tensor array, the values that go in all these tensor objects. We get their answer. Let's dig in a little bit bigger. Here we're going to turn on some logging. So this is going to run again, take a couple of seconds. So let's see if we can understand the logging in the light of the slides we just walked through. So we figured out some memory limit. It's going to depend on your GPU, on your system. We're going to start finding an optimal path. And here we have a path with 32 million elements as the largest intermediate and 36 gigaflops. Here's the path all the way through. Once that's done, we can start creating the workspace to actually do the contractions, create the contraction plan, get the memory allocated, perform the contraction. We see the contraction only took 64 milliseconds because all this pre-work has been done, then freeing up the memory. So that's that step. So we just saw at a high level this pathfinder step, the pathfinding, and then the execution step. So let's just dig a little bit deeper, give some idea of what's going on in these steps. So first, let's compare it. The result we got, just going to run our cuQuantum step again. So if we run this with QIM's optimized Einstein summation notation, it calculates a path. This is just giving the contraction path. It's not doing the contraction. Looks like about 24 teraflops, something like 68 billion elements is the largest intermediate tensor. If we, again, just rerunning our cuQuantum path, here we're just doing the path, we're not doing the contraction. We're down by almost a factor of 1,000 in the computational requirements and a little more than a factor of 1,000 in the size of the largest intermediate. And this isn't to cast dispersions at QIM's Einstein summation. This is vastly better than a naive approach, a greedy approach through that network would be. But a lot of work's been put into cuQuantum, a lot of work that was already there for tensor operations. And we can see that work pays off, a factor of 1,000. We can also see that cuQuantum took a little longer to calculate the path than QIM did. And there's always going to be this trade-off. How much pre-work do you want to do to save on the actual work? And that's just going to depend on your use case and your workflow. But typically, spending an extra few seconds to save a factor of 1,000 in computational cost is probably going to be a pretty good bet. We can let's start playing with some of these options just to give a sense of what they do. So we can turn off reconfiguration, that subtree shuffling step. And if we do that, so basically we set the number of iterations to 0, we get a noticeably worse outcome. The result was faster, but it cost us about a factor of 100 in flops, about a factor of 30 in output size. While we're here, reconfiguration is off, so that's going to keep things stable. We can play with some of the higher level Pathfinder options. So one of the options there is the imbalance factor. How imbalanced do I let these subgraphs get? And I can play with that. The default is 200. I turn it off here. It doesn't make a huge change. If I allow for more imbalance, bumping it up from 200 to much larger number, 800, we do better. We do a little bit broader search of available space, and we get a modest decrease in size, but factor of 10 in flops. Kind of funny that factor of 10 in computational cost is modest, and something similar in memory requirements. So we can reconfiguration. These are options we can play with as well. We can change the number of reconfiguration steps. We can change we can change the size over which we're allowed to reconfigure. This is the number of leaves that we can shuffle around in our reconfiguration steps, and we can see the effects they have. So those are sort of tuning the path finding piece. We can also cause slices. We can say you shall slice this into some number of slices, and that if this will happen automatically if the memory requirements exceed what's available. But we could also do it if we wanted to farm it out to multiple tasks or something. So slices are an option available to you. So there you go. So the largest intermediate goes down a smidge. These are the indices that we're going to slice. We're going to hoist to the outermost loops of the computation. And we could also, as I mentioned, the slicing will happen automatically if the memory required is too large. We can simply tell it as part of the network options what the largest amount of memory available for this computation is, and then the slicing will happen automatically. So if you know your tensor network really well, you may have some specific things you strongly suspect will improve these optimizations. If you're less sure, or you just want the cuQuantum cuTensor network to handle it, we can use the hyperoptimization, which will do multiple samples through here, playing with parameterizations. Some of these options we've seen in others on the Pathfinder and the slicer and the reconfiguration, and play with those and find the best path. And again, there's always this trade-off. Adding more hyperoptimization samples will require more upfront work, but will typically give you a still better result. At some point, we start seeing that there's actually a trade-off between flops and the largest intermediate when we really are getting to the to close to the best possible solutions. All right, so once we have a path such as this one, now we can actually reuse this path and perform the contractions given this path again and again and again. You see, 143 milliseconds sort of wall clock time. So we can do this again and again, reuse that pre-work. These, if you were paying extremely close attention, you may have noticed that I've run contract and the contract path a couple times with the same parameters and got slightly different results. These heuristics that cuTensorNet uses to find optimal paths are randomized. If we want to make sure that we are getting exactly the same path computed through, we can just set a seed, run the contraction path optimizer with one thread, and then we'll get exactly the same path computed again and again and again. And finally, again, you can actually give the contraction an array of values, array of B's in this case, to include in the contraction, and it'll perform the calculation itself. So in this case, it will reuse not just the pre-work done, the optimization step, but reuse some of the auto-tuning pieces of the execution step, which we haven't talked about. And that's pretty much it. We've relied on QSIM's, on QIM's simplification above, so we could see the nice graph, but we don't actually need to. We talked a little bit about cuTensor networks simplification steps here, and cuTensor network will do this. Will simplify as much as possible if the input isn't simplified. So we see here a very similar largest intermediate size and optimized costs even on the unsimplified tensor network. And that's about it. So we've seen now cuQuantum accelerating 3 different quantum computing frameworks, Cirq, Penny Lane, we saw it working alongside with QIM in this example. We saw from Dave's slides that there's actually others as well, but we don't want to, if there's a quantum framework you're using and we don't already support that, that might be something we'd be interested in hearing about. The wide range of problems supported, they all work on these fundamental operations that we aim to support, that we aim to accelerate. And that's it for the labs. We'd be happy to take any questions that haven't already been answered. And yeah, thanks very much for your attention. First part of this question sort of is about memory, and more memory is always going to be better, and more memory bandwidth is going to be better. And so I think the first answer is going to be the A100. On the other hand, the A6000s, if you choose to do these calculations in 32 bits, the A6000 will be, has a lot of horsepower there, and would do a very credible job. Shared memory over InfiniBand or PCI. So I think right now cuStateVec is stronger on the single node multi-GPU case. Tensor Network, well, we saw the example of max cut over an entire cluster, and so that will work right now out of the box with that will work out of the box right now on multi-nodes. The state vec on multi-nodes is being worked on. I'm not quite sure what the state of it is right now. Great questions. What other questions do people have? All right. I think things are winding down. We can follow up with you and email the Martina, if we can maybe email you, would that work? Any follow